let's pick up where we left off, talking about the derivative as a function. And I came across this funny little meme. Somebody sent this to me. This is what you get when you're a math teacher. People send you funny math memes and jokes. So here we've got f prime of x, little kid, and we've got his mom calling him by his full name. So this leads us back into our definition of the derivative as a function. So let's just scroll back to our notes from last time where we defined the derivative of a curve as a function. So this was from last time. So let's just remember that we're talking now about taking our function and defining a new function called the derivative of the function. And this function represents slopes of tangent lines. It gives us slopes of tangent lines to f of x. Okay? That's what f prime of x gives us. It gives us the slopes of the tangent lines at any given x when this limit exists. Okay? All right, so graphically f prime of x represents the slope of the tangent lines. I have it at the bottom here too. Slope of the tangent lines to the curve y equals f of x at a point x f of x. So f prime of x is one of the notations that we use, but we actually have more than one notation for the derivative. And I want to go through a couple of those notations. Some of them come out of the fact that calculus was developed essentially at the same time by two different very famous mathematicians. So let's jump to that and the different notations here for just a second. So here, before we get into the notations, we have to talk for just a second about two famous mathematicians, Newton and Leibniz. And the big mathematical controversy, probably the biggest controversy in mathematics, is who invented calculus. Was it Newton or was it Leibniz? Or maybe they both developed it independently. And it's a fascinating historical story and their personalities and all of it. So here I grabbed a photo of Newton and Leibniz, and it is interesting, and I'll link an article for you guys. And definitely, if you just Google search who invented calculus, you will find all kinds of interesting information about these two incredible men and their discoveries and how those discoveries were published and put out to the public, and who was first, and all those good things. But it is an interesting story if you like history and you like learning about where the sciences and the maths were developed, how they were developed. Looking at these two mathematical minds is very interesting. So who was it? Was it Newton or was it Leibniz? Well, that I will leave up to you to decide or come to a conclusion about on your own. But both of them gave us some of the notation that we use. So we do use both of their notations, and I want to talk about the different notations that are used. So our prime notation is coming out of Newton's work, and that is the notation that we've introduced already. So f prime of x representing the derivative is our first notation that we've talked about. And if we think, just y equals f of x, where x is our independent variable and y depends on that, some alternate notations do come up. So we have our f prime of x, but of course we have y prime. If y equals f of x, we could also just say y prime. And then Leibniz gave us this notation, dy dx. And so this is the Leibniz notation. Looks almost like a ratio, but we don't want to regard it as a ratio. And I do see a little typo right there, not a ration, a ratio. So that should actually say ratio. We don't want to regard it as a ratio, at least not for now. We'll come back to that idea and talk more about what those symbols can mean down the road in a slightly different context. But for now, what we're going to think about is it's implying the derivative of y with respect to x. So we're taking the derivative of y with respect to x, and we're thinking about it that way. In a similar way, we could also utilize Leibniz's notation and say df dx. We can use this notation. This is almost like an operator right here. This notation here, and even this notation, these notations here, is where we actually think of d and d dx as differentiation operators, almost like they're telling us, okay, we're going to do this operation of differentiation or the calculation of a derivative to, and then the following function. So this is saying, you know, this operation here, d dx of f of x. So take the derivative of f of x, or just a capital D next to f of x, d of f of x, or d sub x, meaning the derivative with respect to x of f of x. So those are operators. So these three are representing derivative operators. And these two are coming out of Leibniz's notation. And then, of course, the prime notation came out of Newton's notation. Now, it's not all that important to know which of those came out of, or, you know, who developed the different notations, although it is interesting. It's kind of an extension from this course. But we do need to know that all of these different operations, all of these different notations represent taking a derivative or a derivative of a function. And so, oops, I will keep that. So all of these here actually represent different ways in which we're implying we need to take a derivative or find a derivative, or if we're given a derivative, it could be given to us in any of these forms. So all of these forms are forms that you're going to experience and you're going to see, and all of them mean find a derivative or represent a derivative. All right, one last thing. One of the ways, because if we take f prime of x, if we say f prime of, and we want to find a specific value, we can put a in, and that says find the derivative, right? Of course, that actually means the tangent line. That's the slope of the tangent line. Tangent line at x equals a. When we say f prime of a, when we plug a into our prime notation, that means that's that will be a numeric value that represents the slope of the tangent line right at x equals a. So in Leibniz's notation, the dy dx notation, obviously it's not a function, right? We don't write it as in our function notation with the f parenthesis a or f prime parenthesis a. So the way we do that is we use a vertical line and a vertical line with it's like an evaluation bar, basically. It says evaluate the derivative at x equals a. So these things mean the same thing, f prime of a and dy dx with a vertical bar, and then at the bottom, x equals a at the bottom. So just one more little notation thing here at the bottom of this box is if we wanted to evaluate the derivative, and we're using Leibniz's notation dy dx, if we want to evaluate that derivative at a specific point to find that slope of the tangent line, well, we can use this vertical bar, and the x equals a tells us to plug in a into the derivative to find that slope of the tangent. Okay, so now that we've talked about these different notations, I just want to go back and do a couple more examples. Find the derivative, calculate some slopes. Let's get through maybe 2 more examples on this video using, you know, I'll sprinkle in, I'll pepper in some of these different notations just because we want to start recognizing these as asking us to find a derivative or representing a derivative. Okay, so let's pick up, this is example 4 following from our previous video where we had a few more examples, and we're going to take this function y equals the square root of 2x plus 3 and find the derivative. So we want to find dy dx. I actually use the word derivative in my instructions here. But when we see that, we recognize that that is representing a derivative. That is just our Leibniz notation. Okay? So find the derivative of y with respect to x. And so we're going to come in here. Once we get that derivative, then we'll use it to compute the slopes of the tangent line. So I wrote 4 and 5 just right next to each other, but obviously our whole point of finding a derivative, to actually find a function for the derivative, is so that we can do exactly this, which is plug in multiple values into that derivative to find slopes of tangent lines. So rather than having to compute a slope of a tangent line for each one of those, which is that limit calculation, we're going to do it generically, find a function, and then all we have to do is plug in. So let's get in here and do it. So if we want to find dy dx, so we'll remember dy dx, just like f prime of x, is going to be equal to the limit as h goes to 0, and now we want to think of this as f of x because that's how our notation was. So we're going to do f of x plus h minus f of x all over h, and we're going to calculate that and simplify that down. So this is going to be, since our function is that square root function, this is going to be 2 times x plus h plus 3 minus the square root of 2x plus 3. And we're going to divide by h, and this is going to be the limit as h goes to 0. Well, if I were to try to just plug in h equals 0 here, then I get the same, right? If I plug 0 in right here, each of these roots is the same. So when I subtract them, they're going to go away and leave me with 0 on the top and 0 on the bottom. So again, you know, we always kind of talk about this with limits, right? And this just means I have to do some more work. So what's the work that I'm going to do here? I am going to do, and I'm writing that out here just so that you can see it, but I'm going to go ahead and just erase it right now because I want to use that space actually. What I'm going to do is based on the form of my limit, right? Like we've been working with limits for several weeks now. So when we see square roots, the best way algebraically to simplify this square root is to come in here and multiply by the conjugate and see what happens, because multiplying by the conjugate creates a lot of nice simplification. So let's get in and do that. And we end up with that nice simplification we just talked about in the top. And so in the top I end up with 2x plus 2h. I'm going to do two things at once here. Inside there, I'm also going to just distribute, and then when I multiply the two roots together, the roots cancel, the middle terms cancel, and then I have minus the quantity inside the other two, 2x plus 3, when I multiply the last two terms of that expansion. And in the bottom, of course, I just have h times 2x plus 2h plus 3 plus 2x plus 3. Okay, continuing down in my work here, and in the top I see that I actually get, this becomes minus 2x minus 3, so I have 2x plus 2h plus 3 minus 2x minus 3, so all that's left in the top there is 2h divided by h times the square root of 2x plus 2h plus 3 plus the square root of 2x plus 3. And our h's will cancel. And we end up with the limit as h goes to 0. And notice I am not, and when we're just doing the algebraic simplification, we never drop the limit. We carry the limit throughout until we have actually taken the limit, which we have not actually done as of yet in my work. Okay? That's going to be my next step. So until this point, that limit needs to carry throughout. Okay, now as h goes to 0, we actually only have one h left. This term goes to 0, so that term goes to 0. Let's do that in red. That term goes to 0. The 2h goes to 0. And notice in the bottom I have 2x plus, now I'm actually taking the limit. This is where I drop the limit notation. And notice in the bottom I have 2x plus 3 plus another square root of 2x plus 3. And so this ends up being 2 over 2 times the square root of 2x plus 3. And these 2's are going to reduce, and I'm going to end up with 1 over the square root of 2x plus 3. All right, so there's my full limit calculation that gives me dy dx. So dy dx, remember, represents the derivative f prime of x if we're using the prime notation, the Newton notation, but we have found our derivative. And it is always useful to just remember, and I'm just going to keep reminding us, that this now represents a function that gives us the slopes of tangent lines to y. Okay? And y was the function, the square root of 2x plus 3. Okay? So we'll actually write in that function. So at any point, this function, when this function exists, right, on the domain of this function, which it does have some domain restrictions because we have a root here, but as does this, right? This function itself has some domain restrictions that we're working with. Its derivative also does. But when that function exists on its domain, it represents the slopes of tangent lines to the curve y equals the square root of 2x plus 3. Okay, so that was using Leibniz notation, the dy dx, but now we are asked for, that was actually, I'm sorry, that was the answer to number 4, but 4 and 5 go together. These two problems go together. So now let's find, I called it g of x here, but I'm going to say to y. Now let's find the slopes of the tangent lines to this curve y equals square root of 2x plus 3 at 1, 2, and 3. So if I want the slopes of those tangent lines at 1, 2, and 3, I have, this is like the beauty of having a derivative. Now, to find the actual slopes, all I have to do is plug those in. So it was at x equals 1, x equals 2, x equals 3. If I want to find those slopes, all I have to do is use my derivative and plug those in. So I'm going to just take dy dx. Now, just as a reminder on the notation, if we want to evaluate dy dx at 1, we can use this vertical line that says evaluate the derivative dy dx at x equals 1, and we can just plug it in. So this is going to be 1 over the square root of 2 times 1 plus 3, or 1 over the square root of 5. Now, if we don't like that root in the bottom, of course, we could rationalize and we could get the square root of 5 over 5. Either of these is fine. I'm gonna just run through the rest of these. Dy dx, when we evaluated at x equals 2, would be 1 over the square root of 2 times 2 plus 3, 1 over the square root of 7, or root 7 over 7. And if we want dy dx, and look at how fast this is. I don't even have to do a limit calculation because I have a function. Like, we created a function. So 2 times 3 plus 3, which is 1 over the square root of 9, or 1/3. Okay? And there are the slopes, my 3 slopes of the tangent lines at those 3 different points, 1, 2, and 3. Okay, let's look at one more example. Okay, so let's find, so again, just playing around with the notation. So let's find dy dx of evaluated x equals 4 of y equals 2x minus 1 over x minus 3. Now, there are a couple of ways that we could write this as well. Like, rather than just using that Leibniz notation, I could even say take the derivative with respect to x of 2x minus 1 over x minus 3. So let's play around a little bit with that derivative operator notation. So that's representing a derivative operator. Telling me take the derivative of this function. Okay, so if we're going to do that, we're going to be taking a limit that will equal, let's write one more thing, that will give us, these are all equal, dy dx. And to find dy dx, we're going to take the limit as h goes to 0, and now we're going to plug in x plus h. So I'm not going to rewrite the derivative, we've written it enough times, I think. So we'll just jump right into this. So the definition of the derivative, and we're going to have some algebra to do on this one to calculate that. So f of x plus h minus f of x all over h as h goes to 0. So taking that limit. So again, we're trying to find a function that represents the slopes of the tangent lines. That's what this is going to give me. Ultimately, this dy dx is going to be the slope of the tangent at x equals 4. And so to do that, of course, we're going to go to that definition of the derivative, take that limit. So here we've got that limit. We need to simplify it, right? It's all kinds of a mess. If I were to try to plug in 0 right now, I'd get 0 over 0. So, I can see that that's going to happen because if I plug in 0, I have the same 2 fractions in the numerator. And so I know I'm going to have to do some more work. So we're going to have to get in here, simplify it. Let's definitely find a common denominator between those 2 fractions in the top. I see 2 fractions in the top, definitely want to get them into a single fraction to simplify. So the common denominator here is going to be x plus h minus 3 times x minus 3. So let's multiply both of these fractions by a ratio that will create that common denominator. So let's get in there and do that. That's going to involve some expansion. So let me get in here and get it all on the screen. So let's see. What do we get up here? So in the top, I have 2. I'm going to distribute a couple things here. So 2x plus 2h minus 1, and then I need to multiply by x minus 3. And then I need to subtract 2x minus 1 times x plus h minus 3. And all of that is going to be over x minus 3 times x plus h minus 3. And then we're dividing by h, but rather than writing division by h right there, dividing by h is the same as multiplying by 1 over h. Okay? And so I'm going to simplify that down on this line and erase this. Okay? It looks like an n, h. So I'm going to get that simplified. And now I'm going to expand. So let's get these, let's see what these expansions look like in the numerator. And we ought to have a good amount of canceling once I get done. So we've got 2x squared minus 6x plus 2xh minus 6h minus x plus 3. And then expand the other two polynomials here. So we've got 2x squared plus 2xh, see if I can get it all on the screen, 2xh minus 6x minus x minus h plus 3, all divided by h times x minus 3 times x plus h minus 3. Sorry, I had to chuckle because it's taking up such a long space there. Okay, let's see. Then in the numerator here, let's go ahead and, I'm going to, obviously, there's a little bit of simplification, and I'm going to distribute the negative. So this is minus 2x squared minus 2xh. This becomes a minus 7 here. So we end up with a positive 7x there. And because it was a minus 7, and then distribute the negative, plus h minus 3. Okay, all of that said, now I can get some canceling. So now I come in here and the 2x squared and the minus 2x squared are going to cancel. Notice that I have a minus 6x. I have a minus 6x and a minus x here, but then I have that positive 7x over there. So those two will cancel with that 7x. I've got a 2xh, cancels with a negative 2xh. I have a 3 and a negative 3. And so look at all of that. And what I have left here is a minus 6h and a plus h. That's literally all, this entire huge expansion that I had has canceled, and I have minus 6h and plus h. So this is going to become the limit as h goes to 0 of simply minus 5h on top over h times x minus 3 times x plus h minus 3. Now the h's are going to cancel, and I end up with the limit as h goes to 0 of just negative 5 over x minus 3, x plus h minus 3. Okay, whew, that was a lot of algebra right there. So now let h go to 0, and our dy dx, derivative of y with respect to x for that function, as we go to 0, right, as this goes to 0, as h goes to 0, let's do that in red, as h, actually notice that my limit, right, the whole way, my limit carried throughout because I was not taking a limit, I was just doing algebra. Now I'm taking a limit. Now I'm actually doing the calculus, letting h go to 0. As h approaches 0, that term becomes just x minus 3, so there's 2 of those x minus 3's, and my derivative is minus 5 over x minus 3 squared. And that is my derivative. Now I was asked to compute the derivative at x equals 4, right? So now let's finish it out because that was the actual question. Find the derivative at 4, which is the slope of the tangent line at 4. So to finish that out, dy dx evaluated when x equals 4 would be negative 5 over 4 minus 3 squared, which is 1. So the derivative at 4 is negative 5. And remember that that represents, right? And it's like I keep probably sound like a broken record, but remember what that represents. That is the slope of the tangent line to y equals 2x minus 1 over x minus 3 at x equals 4. Okay? That is what that represents. That is a slope. It's a negative slope, so that would actually mean that that function y equals 2x minus 3 over x minus 2x minus 1 over x minus 3 at 4. If we were to zoom in on that function right at x equals 4, it would be decreasing at a rate of negative 5 over 1, at a slope of negative 5. Okay? Slopes are rates of change, and so they're telling us what's happening to the function at that point. All right. So let's see if we can get that our other examples kind of there at the bottom. But that's that whole example, the algebra and the calculation of the slope. So I'll close this video out where we started this video. F prime of x, we could call this little kiddo, he has a second nickname as well, right? He's got a couple nicknames. We could call it dy dx too. We could call him dy dx if we wanted to. But of course his full name, full definition is the limit of f of x plus h minus f of x over h as h goes to 0. So we do need to know that definition of the derivative and how to find it and how to calculate it and apply all of our limit techniques to do that. So we'll leave you with our funny little calculus meme here.